Linear's fun. But then so's this. I want to keep going with our graph ideas. I want to talk about some more development pieces in there. So I have a graph with a set of vertices and a set of edges. Let's take an edge, denote it by the two vertices, and rather than actually put set brackets or ordered pair or anything like that, I'm just going to write the two letters next to each other. So this is the edge E. It connects U and V. So in a very Mr. Rogers sense, we have a neighborhood. U and V are neighbors. They're adjacent vertices. And E is the edge joining them to one another. The edge is incident to each vertex. If I have two edges that both connect to the same vertex, those are adjacent edges. So adjacency means being next to each other. But vertices then have to have an edge between them. Edges have to have a vertex between them. As I said on Monday, pictures are a lot easier than lists. I can give you a giant pile of vertices. And a pile of edges. This is helpful? This doesn't make a damn bit of sense. Just looking at this, I don't see very much. So I'm going to cheat. Here, I've laid out my 5 vertices. Drawing the appropriate edges. Now I will say, I labeled my vertices from top to bottom in order. So U, V, W, X, Y, U, V, W, X, Y, top to bottom, left to right. I laid out my edges in a similar order. The first letter gets bigger as I go from left to right. The second letter gets bigger as I go from left to right. So UV, VW, VX, VY, WY, and XY. Ta-da! All 6 of my edges. If I asked you to take some of those edges away, anywhere between 1 and all of them, you could do that, right? You could make another picture that had fewer edges. If I keep the same vertex set and I take a subset of the edges, I've created a subgraph. Now, please notice, I have left the possibility there that you could keep this graph exactly the same, because it says here subset or equal to, right? So a proper subgraph requires me to get rid of at least one edge. Contained in and not equal to E of G. Page 10, we have several options. Now, please notice, if I don't have anything with U, I don't need it, do I? U is not adjacent to anything in H, is it? Which tells me that I think I made a typo in the note I wrote. And I go back and I look and I say, yes, I did. That should not be equals, that should be subset equals. So I can get rid of a vertex as well. All of these on page 10 are different subgraphs of the graph we are working with. If the vertex set stays the same, that's usually referred to as a spanning subgraph, but I don't like that term because spanning has another meaning that we'll use later that I think is more appropriate. So let's look at a subgraph. We'll use the same subset notation idea for a subgraph. If I have a graph G, I have a subgraph F. We're going to define an induced subgraph. By saying, if the edge is in G and I keep the vertices, I have to keep the edge. So we go back to that picture on page 10 for a second. If I take this picture and I only keep W, V, and X, picked a set of vertices, what's the induced subgraph? So same picture as above is where I'm starting. From this, just keep those. What's the induced subgraph? Yeah, what's the picture look like?
It'd be the line, it'd be like the top half of the triangle.
And that's it, right? It's going to look like that. On the other hand, if I give you a subgraph, you should be able to tell me, is this induced or not? So here's another subgraph. Is that an induced subgraph from the graph we started with G? It is a subgraph of G. That is not definitely true. But is it an induced subgraph? Why not, Lauren? And I kept both vertices V and Y. If there's an edge connecting them in G, there has to be that edge connecting them in here for it to be induced. I have to keep all the edges between the vertices I kept. I threw out Vy, so that's not induced. But notice what I did in the first one is I gave you a set of vertices and said induce from this. So that top one where I said V of F is VWX, that's the set I'm talking about here. If I want to induce from a set, I give you the set of vertices and say, here, figure out what the appropriate set of edges is to keep. Quite frequently, we'll say, oh, this is from G, so I'm going to call it G restricted to the vertices in our set S. So the subgraph induced by S, part of my graph connected to my set S. If I can do it for vertices, I should be able to do it for edges, right? So here's a parallel definition. The edge-induced subgraph consists of all the edges you named and then all the vertices they touch. You have to touch at least one edge in X to be the edge-induced subgraph. Sometimes instead of G of, you'll also see this written the set S part from G. Similarly, down here, you'll see the set X part from G. It's just an alternate notation for the same thing. This textbook, I believe, uses the first one, but I found this one in 2 different online resources. Again, there's another picture on page 10 that shows you 2 edges. So I want these edges, well, then I only get the vertices that are connected to those edges. What's that mean again? So you have to say, I'm inducing on at least one edge. I'm inducing on at least one vertex. I can't just say, here, induce on nothing. What do I get? A problem, because the graph has to have a non-empty set of vertices. So this is starting with a graph and taking things away or deciding what pieces we want to keep, right? If I specify what things I want to throw away, I can subtract from a set. So let's take some edges and throw them out. I use a subtraction. Remove those edges from the graph. I take any subset and I throw them away. If you actually give me a list of edges that these are the ones you want to throw away, I could use a set bracket here and list all of those edges individually. So if I throw away an edge, I don't just squat to the vertices. But if I throw away a vertex, I throw away every edge incident to it. So I can take away an edge without changing the vertex set, but I can't take away a vertex without changing the edge set, unless that vertex had nothing connected to it at all in the first place. If I have a vertex, doesn't have any edges, and I take it away, I don't change the edge set. If you've got anything connected to that vertex, you take the vertex away, the edge can't just float out there. It isn't like a hair or a cilia on some cell, right? No, it goes. Questions? It's all terminology at the moment, I promise. We're just got to get all the terms down so that when I say something, you don't go, what the do you mean? If adjacent means there's an edge between them, non-adjacent means there isn't. So if I have non-adjacent vertices, then the edge UV is not part of my edge set already. Yes? I could take things out. I can put stuff in. So I can add another edge to a graph if I want to. Literally adding the edge UV. The only thing I change is the edge set, vertex set stays the same. Questions so far? Traversing, moving on a graph requires me to describe to you what I'm doing, how I move from place to place to place. Place, therefore, is a node. I'm going to move from vertex to vertex to vertex. I need to tell you what edges I'm taking, right? So, a walk, a UV walk, call it W, in a graph G, is a sequence of adjacent vertices. It starts at U. So W will be an ordered set. U, we'll call that V0. And then we have V1, and they have to be adjacent. So there has to be an edge, V0, V1. Then V2, and so on until VK minus 1. VK is my ending vertex V. So I started at U, I went to V. Here are the stops I made along the way. The edge, VI plus 1, has to be part of my edge set for me to be able to do this. So the edge V0, V1, the edge V1, V2, the edge VK minus 1, VK. I don't have to worry about VK, VK plus 1. I didn't go any further than that. Each vertex lies on our walk or belongs to our walk. What if U and V are the same vertex? Start here, I end here, right? I've made a closed walk. Otherwise, I have an open walk. That should sound really familiar. Open curves, closed curves. Drawing, we did all of this sort of stuff. The length of the walk. The length of the walk is the number of edges, not vertices. However, what's the difference between the number of edges and the number of vertices in my walk? Look at the walk, the way we wrote it out. How many edges do we have? Beg your pardon? That was my walk. It went from U to V. There are K edges, right? 1, 2, 3, K. But there are K plus 1 vertices because I started at 0. Now, sometimes we don't even bother to write it as an ordered anything. We just write, V0 to VK as a list. There is one, I think, rather contentious issue here. Any chess players in the room? Play chess? One of the worst things you can get to in chess is a draw where you put the person in check, they move to a safe spot, you put them in check, they move exactly back to where they were. I just go back and forth and back and forth and back. And the game can't end. Stop. What if I repeat parts of my walk over and over and over and over? To do that, there's nothing in here about repeating edges or repeating vertices or what's allowed and what. I could just walk my graph and walk back and forth between two vertices until I collapsed. Not enough out, it won't take long. All right, then let's make a new definition. A trail. A trail is a walk that does not repeat an edge. Page 12, figure 16. Here's a walk. X, Y, V, Y, W, V. Sorry, VW. Is it a walk or a trail? Or both. Because if it's a trail, it's a walk, right? What is it? A walk or a trail? Let's check. I go from X to Y. I go from Y to W. Up. I go from W back to Y. I repeated an edge. There we go. On the other hand, U, W, Y, X, W, V. I think that's a trail. Is it? U to W, W to Y, Y to X, X to W, W to V. I never crossed the same edge. I did hit the same vertex more than once. But notice my definition of trail only talks about edges. So a trail only investigates whether or not we repeat an edge. Well, then, what if I don't want to repeat vertices? Well, we'll call that a path. So I have walks, trails, and paths. A walk can be anything. A trail is not allowed to repeat an edge. Path not allowed to repeat a vertex. Question. If I give you a path, must it be a trail or not? Could you make something that is a path that is not also a trail? Shaking your head at me, Mia. Think out loud. It's allowed.
If you hit up once, you would have to hit it again for like an issue.
In order for me to go over the same edge twice, I'm going to have to start on one end of that edge, go to the other, and at some point, either go the same way again, which means I hit this vertex twice, or go back, which means I hit this vertex twice. If I miss hitting a vertex more than once, I can't hit an edge more than once. Every path is a trail and a walk. Every trail is a walk. It goes this way. We made them more and more restrictive. Now, we listed our walk, we called it W, and we listed out all the vertices. If I'm going to specify that I want this to be a trail, I'm probably going to call it T. If I'm going to specify its path, I'll probably call it P. But I don't care what you name them. You can name them Fred and George for all I care. You just have to tell me what kind of item we're looking at. Oh, the path, the walk and the trail that I gave up there were both of length 5. There are 6 vertices listed there. That means there are 5 edges listed there. If a walk, a trail, a path has length 0, we call it a trivial walk. You didn't go anywhere. We'll use that as a base for some induction arguments. Is this property true if there are trivial walks? If it isn't, then it's not going to be true in general. So we'll see trivial walks come up again. Questions so far? I'm going to say something that's going to sound very familiar to those of you either in abstract or who have already taken abstract. If I have things, I can operate on them. I need an operation for walks. I did this walk. I do this walk. Put them together. Concatenation. I'll steal from the CS people. So if I have a walk that goes from U to V, and then I have a walk that goes from V to W, when I concatenate them, when I do one after the other, I get a UW walk. So it's really like adding, right? I do one, then the other. I get a joined walk. But what if you have 2 trails and you add them? You get another trail? Why not, Reese? You shook your head at me.
VW and some of those in V and walking on the trail.
I don't know anything about what pieces and edges are in the first one, what pieces and edges are in the second one. If I concatenate them, I may end up overlapping an edge or overlapping a vertex. So the only thing I can be sure of is that when you add paths, you get a walk. When you add trails, you get a walk. You might get lucky and get a path or a trail again, but you don't know. So again, stealing from my abstract language and my discrete language, this is not a closed operation. Those of you who haven't gotten there in abstract, we will soon. And my ideal image of this is if I go back to that picture we had a moment ago, I'll give you two paths. The first path is U, V, Y, X. The second path is X, Y, V, U. Those are both paths, but if I add them together, I only get a walk. It would be nice if I knew that I could find paths as opposed to just finding walks or trails. Path is more efficient, right? I'm not repeating any edges, I'm not repeating any vertices. It's the fastest in some fashion, perhaps. It's at least a non-repeating thing. Excuse me. I claim if you've got a walk of length L from U to V, then you have a path from U to V. It can't be any longer than that walk. At least you're nodding. This makes sense?
Yeah.
How would I show that this is true? This is a claim. A claim requires a proof.
If you had like a walk, like drawn out, if it was a straight path and any vertices, and would be a path, but you can't like go any longer than that without repeating vertices. So the longest it could take to be a path and walk would be that like.
Yes, I think. I'm just not sure I like your explanation yet.
I mean, if you had like three circles, 1, 2, and 3, and your walk was like 1 to 2 and 2 to 3, then your path could not be any longer than those two edges because you would have to repeat something else to get a bigger length. But doing that, you would have another vertex.
Right, but notice you started with I have a path.
It could be
Okay, but if I'm starting with a walk, how do I know I have to be able to find a path within that walk? So I think I agree with you, but now I have to figure out how to write this down so it makes more sense because we're close. It should. It also may contain fewer vertices, right? But if I start with a walk and I make that walk as short as I can, then the only thing I could do is take away pieces from it to make a path. If it isn't already a path, then it's either got to have some back and forth or it's got to have some loop in it, right? And I can just cut those off. We will not spend a lot of time writing out formal proofs, but I at the very least want to get some sort of a visual argument so that you can make those similar arguments to me later. This is in the text, that's theorem 1.6, and they have a formal proof written. I don't want to rewrite it in the next 4 minutes. That seems like a waste of time when you can go look at it. But the idea is I say, okay, here's a walk. Let's make it the shortest possible walk from point A to point B, from U to V. Well, then it's the shortest possible walk. It's got And every time I run into something that I repeat, you either say, well, don't do that repetition, or if you went back and forth, just go one way and stop. If you went in a loop, cut that loop off, and now you've made the length smaller. And that means that the length of the path can never get bigger. It's got to keep getting smaller. Okay, two more terms. A circuit in a graph is a closed trail. By definition, a closed of length 2 would have to go back and forth across the same edge, wouldn't it? Which means you can't have a trail of length 2 that's closed. So your trail has to be at length at least 3, be closed to make a circuit. A cycle in G is a circuit that's only repetition is the start end spot. So in one sense, you could think of those as the beginning and end spot, which happen to be the same, but that means you're never allowed to repeat any other vertex. Those of you that took Calc 3, if you think of this as a curve, it means it never crosses itself. A simple closed curve on a graph. So those two are going to be my primary methods of walking around and figuring out lengths and distances and things. A K cycle has length K. A K circuit has length K. Surprising no one, I hope, a 3 cycle is called a triangle. It's 3 edges. I like that. Unfortunately, we don't tend to use the rest of the shapes. You don't call squares and pentagons. It kind of fell out. But triangle is actually going to be something we use frequently. A cycle is even if its length is even. A cycle is odd if its length is odd. If you remove a vertex from a cycle, you get a path. Because nothing's repeated. I'll pick up the rest of this section on Friday. So we finished section 1, but we haven't finished section 2. I will see you all then. Have a wonderful rest of your day. Which one, Stas? The start end vertex. You're very welcome.